So my name is Anaïs Lacoursière. I'm a research scientist for DFO. Thanks a lot for the organization of this great event. It's awesome to see how the community is growing so fast. How many archivists that's our yes.
This should work. If not, then yes.
Okay, so I'm here today to present about GOTeDNA, which is a new DFO initiative in close collaboration with main eDNA. So GOTeDNA aims to centralize the guidance on optimal timing for eDNA. Oops. Okay, so some just DFO internal background. So a few years ago, we were asked by manager to provide robust guidelines and standard reporting to help managers to take decision on eDNA policy, any type of policy, just some more confidence on the data itself. So we provided this reporting template, some guidance, general guidance on how something designed should be how eDNA studies should be designed, but also how to interpret results. So we provided some biological factors that needs to be considered, life cycle, abundance, population abundance, and physical factors. But in fact, that this advice, this PISCeS document is still very broad, and it's very difficult for anyone that is using it to really know how to use it for a specific species and how they can adapt it for a specific region. So I led the eDNA session on OBPS last fall. Sorry about that. And it was a good opportunity to basically send a questionnaire to see how the people are designing their study. How do they do that? There are so many publications out there, but it's we know there's regional and biological factors that needs to be considered. So what is interesting I found is that first, most of the people are piggybacking. They just collect water samples because it's easy based on their traditional sampling. So it was based on the discussion. When you look at the questionnaire, it's basically 36% of people say, well, we need more guidance for specific taxa in specific region. And there's 29% of the people saying, well, we really need more more knowledge gap about biological and physical factors that can alter the optimal detection in designing proper studies. So in fact, is that there are a lot of studies that are collecting samples right now in the suboptimal periods, and there's probably a lot of false negative only related to that. So even if you have a perfect lab methods, you can really miss it. And that's a lot of zeros value, that's a lot of time spent. And when people are some people have the chance to do some pilot projects, some people don't, they do some ad hoc assumption. So it's very hard. The bottleneck is that it's just very hard for people to know when they should go in their specific regions for specific questions. So GOTeDNA basically tried to provide some guidance on when to streamlining the process of trying to find the optimal detection period. So how do can we get there? Obviously, if we have a better understanding on the how it changed time quality, that will also help us to interpret results over time. So life cycles is due to life cycle when you see changes in your detection, eDNA detection or abundance or different biological and physical factors. Hopefully we can have something streamlined where it also helps to design studies consistently, so going on best practices and having some guidelines how to get there. And hopefully managers will have a better understanding of variation, interpreting variation in our data, and using and better communication that will be a tool to help communicating to results to managers. So the first step we started a year ago was to basically do a data report. How do we combine data? How do we combine observation between regions and taxa? So we basically put a lot of combined data together, and for that we were a large group of people. We're trying, projects are very different, they're using different primers, there are different filters. So we put a lot of efforts on finding criteria where you can combine data and some when we cannot combine data for optimal detection, specifically for optimal detection periods. So we found those and we basically divided those project versus sub-projects. So sub-project can be combined together for suboptimal versus project that it should be kept separately. So by doing the criteria all together, as defined as a group, we had 30 data sets, and we're able to combine them in 13 projects. So that gave us a lot more power to see the optimal detection periods if we can combine our observation. So there was the first step to be able to compare our data between regions. So we did it by eco-district at the genus level. So basically, by going back, even if it's at the district scale, spatial scale, and only at the genus, it's still 200 pages long. So here comes the idea of having some things interactive where people can basically have the details of what they really need for designing their own studies at the taxonomy level, but also at the regions. So first, the idea is that the users can go online. They will have a pop-up window. We understand that a lot of people don't have a lot of background how to interpret results, so the communication and the maximum, how they should use the data is very important. So the model behind the advice include the intra-annual variations, but also the consistency of these optimal detection periods between years. And obviously, we are hoping that the models will very well define when there is no optimal detection. So this is good. This will be great to just know when you don't have to board with the fact that you have two samples at that season, but you can also compare different projects if their samples have been collected in different periods. Okay, so that's just mock-up, so it's a very simplified way to present GOTeDNA. So basically you have the users can select if it's the species-specific approach or they want to observe metabolic coding. Then they select the file, the taxonomy level that they want to visualizing, and then they have the regions that they're interested on. So then in the observation window, you will have the results from the statistical models. So when is the optimal detection period? What's the confidence value related to the data that are available? Is it high, is it very low, or we don't know, there is a lack of data. And then you can visualizing the time of the variation in your data between months, between year, but also between primers. So here's an example for Cargill sharks. So it's just in the data assembly, and you can see basically that even if there's eDNA persistence, it's still, you still need to consider the migration pattern. If you don't go the time when the species is there, you just lost the sign of the species. So this is another example where you have chimicates. So they have been successful to detect chimicates in summer using qPCR primers. If you then go on another project where we did the metabar coding each month for a couple of years, we detected them more frequently, so the detection rate was greater at the end of fall, that matched with the biomass. And then when they die, they basically shed this eDNA during winter, so you can detect them when they die, basically. So you have a high detection time. The other window will be the data. So for the moment, we're thinking about just providing the minimal data and the link with the published data, so that can be linked directly, or you can have the emails and you can just email the person. So basically, that's depending if it's published or not. And that's fully at the discretion, basically, of the person using it and what we can share or not. Ultimately, our goal, the vision, is to have a predictive model. So if we can, obviously we will not have observation for all the regions. So the idea is if we start to combine all of the data, we can, at some point, we'll be able to predict based on the biological and physical factors. So for example, in the Arctic, under the ice fiber, for the moment what we observe is that there's a higher detection period in the longer period because of the ice fiber. So the DNA is well preserved there. Okay, so basically there will be a window. So that's the vision, the future, hopefully. So that's having a prediction windows where the confidence will increase and the prediction will increase over time if we're combining observation. As I said, the only way to get there is to combine data. So I think that's a good fit with the station there and the importance of all of the other incentives. If we start to combine our data together, so we can start to have a better confidence and we can start to think about the predictive model. For us, we have worked a lot with main eDNA. That's strategic. I'm working for DFO, and obviously if we are using, there are a lot of integrators that are in the main, they are not in Canada. So if we are able to know when is the optimal detection, we can basically make sure that our symptom design in Canada will be well adapted, even if we don't have the data yet in Canada. There's also a lot of northern migration that are expected in the future, so we can basically make sure that we'll interpret the results in the future properly. And recently, Anna, who's in the room from PISCeS Canada, has also joined the project, so we can pull all the Canadian data together and hopefully open the door to other international collaborators. Okay, so the first challenge was to combine data. So we developed data, metadata templates and pre-populated from the methods. And then we saw GBIT a few weeks ago, and it was like, oh wow, they did a really good job. So basically we want to make sure that obviously all of the wording and how we can use all of those international database, and that GOTeDNA can be linked on those international initiatives. Okay, so we want to attract people by doing a strong statistical model. So we want that the people are using it. They import their data, they want to import their data because they want to know their optimal detection periods. So if we are, so the people, we realize that a lot of people cannot or don't want to publish their data until it's published or somewhere else, or they do have other restrictions, but they can basically select if you want the data public or not. So you can use it just as a public tool, as a statistical tool, and then you release your data, and then that becomes in the machine learning of the GOTeDNA. And obviously that's much easier to publish your data when your project is done. So that's basically the proof of concept. You know, we really try our best to think about how that can be helpful, how we can move forward, and how we can develop a tool all together and combine the data. And what's the purpose and all of the application if we're combining data, the power of it. Thinking about Gene Bank and Bold, if they will not have combining all of the sequences in years ago, we will not just be here today. It's because they have been combining all of the sequences that eDNA can start a couple of years ago, and this is because there was a successful data management behind that. Okay, so the take-home message, basically GOTeDNA aims to provide a standard way to provide guidance on optimal timing and learning from other regions. We are dependent on the proper data management. We thought that we're blocking in a different way for many reasons. So we need to think about that, how we can apply that. It's a research project, so we are working on the implementation plan, but we don't know yet who can import, we can make sure that it's well maintained and well adapted and accessible for everybody. So we're working on that as well. So I'm happy to have any discussion with you regarding how we can move forward and making sure that this is a useful tool for everyone. Just want to say a big thanks for a lot of people in the room who have shared their data. So this is great. I think it's a good collaborative work. I also want to big thanks for eDNA because we brainstorm openly to which data set can be combined, which data set cannot be, how we can provide that, the visualizing, having different perspectives, different people with different backgrounds, and how we can communicate those results. And finally, big thanks to the northern communities because they're collecting the samples in the last decades for that project. So we have more than 10 years data set for that. So that's great. Thank you very much.